So we know now how to kind of prove that a differential equation is going to have a solution. There's going to be a function that satisfies that differential equation. And now we're going to look at something that's a little harder to prove, and that's going to be, how do we know whether the solution is the only solution? Having only one solution is really nice in a lot of situations. For physical systems, it means that we know exactly what's going to happen. We don't have to worry about potential multiple things that can happen. When we're just solving things by hand, uniqueness is really nice because it means we're done. We don't need to look for more solutions. We know there's only one, which is very, very nice. And so what we're going to do actually is just go back to our existence theorem, and we're going to add a couple things in these blanks that we left. So we're going to say, let's combine this. This is now the existence and uniqueness theorem. So if we have one extra condition, that's it. If we have one extra condition, then the conclusion is that we have a unique function. That's all. That's it. There's only one thing that we need. And all that is that the partial derivative of this function with respect to y is also continuous. So I'm actually going to change this is to an r. Or maybe you could do like is and then like r like that, depending on whether you're looking at the existence part, the uniqueness part, or both. Okay, these theorems are often combined. Okay, so that's it. If the partial derivative is continuous, then great. And maybe you haven't seen partial derivatives before, but if so, if that's the case, a partial derivative is pretty straightforward. Let's say I have a function, like maybe I am looking at a function that is like, I don't know, t squared sine of y, or something like this. The partial derivative with respect to y, they look kind of like sixes. We call them d. I forgot exactly what they're called. But anyway, this is the partial derivative with respect to y. Instead of d dx, this is d dy, but it's like a different kind of d. A lot of times we'll say partial y. Anyway, it's basically just treat t and really any other variable as a constant. So if we had the regular derivative, if we had d dy, right, we'd have to use the chain rule here as well as the product rule. But the partial derivative says I'm going to treat every other variable as a constant, and so it's just going to be t squared cosine of y. So partial derivatives are easier to take than normal derivatives. You essentially just kind of treat every other variable as a constant. All right, so if the partial derivative with respect to y is also continuous, then that solution is unique, which is really nice. So over here, we had the existence of a solution, and we knew it was unique too, right? Because what is again, this is our f right here. What is partial f? Partial y? Well, the derivative of this with respect to y, right? Just treating y as the only variable is just 2y. That's certainly continuous. So we know it exists and is unique, which is useful. All right. So a couple other things is that there is another way of kind of talking about uniqueness. And another way of talking about uniqueness is that you could say if y1 of t and y2 of t are solutions, then they're the exact same thing, which kind of sounds a little silly. But this is another way of talking about uniqueness. And this way is actually really useful a lot of times, okay? Because a lot of times we might have two different solutions and there might be unknown things about them. And if we prove that the solution's unique, we say, oh, these are actually the same solutions, even though they might not look the same, or even though we might not know everything about them, that tells us things about them. So we will use this formulation sometimes as well for uniqueness. And then again, just as you can see out here, right, existence was easier to get than uniqueness, which means uniqueness is going to be easier to break. Existence just required that that right-hand side, the dy dt, is continuous. Uniqueness will require that its partial derivative is also continuous. So it's an extra layer of requirement here. But let's see what this might look like. How can we use this existence and uniqueness theorem? It's going to have us consider dy dt equals 3y to the 2/3 power, and our initial condition, a very common one in a lot of times, and it's also very simple. Initial condition y of 0 is equal to 0. So does a solution exist? Well, we can find that out by saying, well, this is our f of t comma y. Again, it's autonomous. Autonomous equations are simpler. And we actually spend the whole next section talking about autonomous relationships, autonomous differential equations and what we can do with them. So we'll be really unpacking the power of autonomy soon. But yeah, right? This is a continuous function. We only need it to be continuous in some rectangle, but here it's continuous everywhere. Yes. We have the hypothesis of the theorem satisfied, so we in turn are granted the conclusion. But what about uniqueness? Well, let's look at the partial derivative of f with respect to y. And if we take the derivative of this white part with respect to y, what do we get? We get the power rule. The 2/3 comes down, we subtract 1 from the exponent, and when we simplify this all out, right, we get 2 divided by the cubed root of y. And this is not continuous for all values of y. Specifically when y is equal to 0, right, we shoot off to infinity. So that's a break in continuity. So it's not continuous for all y. And specifically, the partial derivative is not continuous at our initial condition. All right. So we do not have, we're not guaranteed uniqueness. Note that the conclusion is not that there is not uniqueness. There's no conclusion. We're not guaranteed uniqueness. I thought of a better example, right? I say, like, you know, if you don't do your homework, oh man, maybe I just lost it again. If you skip your homework, you know, I'm not going to give you $5,000. That's true. If you don't do your homework, I'm not going to give you $5,000. But that doesn't mean that if you do your homework, I will give you $5,000. Okay? I would love for you to do your homework, but, you know, I don't think that's quite legal either. Anyway, so, or maybe legal. Certainly does not follow college policy, I think. I think that might be breaking some things. But maybe it'd work for you. I don't know. All right? So we don't have uniqueness guaranteed. But it still might be unique. Who knows? Again, I want you to pause the video and solve this differential equation by integrating. So pause it now. Once you've paused and solved this out, you should get your solution of y is equal to t cubed. Again, you're going to get the constant is going to be taken care of with this initial condition. Is that the only solution? That is certainly one solution. But let's talk about the equilibrium solutions. Notice if we look at equilibrium solutions, we get that, yeah, there's an equilibrium solution of y equals 0. So we have two different solutions that satisfy this initial condition. And that's a little irritating. Let's look at a slope field of this. Again, we don't have uniqueness. All right. Let's look at a slope field that models this initial value problem. So over here, if I go and say, all right, we have 3 times y to the 2/3 power. We get a slope field. Let's clear all this. Right? We can see this, that, you know, we start at 0, 0 roughly. Oh yeah, the t cubed. That's great. But also, right, we have another solution here, and I'm going to slightly change what this looks like just to make it easier for it to show up. This green graph, which is much harder to see, is also a solution to the same initial condition. So it's not a unique solution. There's multiple solutions. Another way of seeing this, as we'll talk in the next video, is that the solutions cross each other. Now, if we have uniqueness, solutions will never cross each other, which is really powerful. All right? But uniqueness fails here. We can't guarantee uniqueness, so the solutions cross. All right? And so I want to be I'm going to be very clear about, right, this is breaking uniqueness, right? The solutions are crossing is kind of an informal way of thinking about it. This is a lack of uniqueness. There are two functions that have the same initial condition. But what uniqueness is not, remember, is I think some people, it's very easy to confuse this with like the vertical line test. If dy dt is equal to the sine of y, right? Remember we had like some solutions that would go here, some solutions that would be repeated, right? And even though there's like a bunch, you see a bunch of solutions, these all have different initial conditions. These solutions will never cross each other. And there are equilibrium solutions that will get close to the other ones, but they'll never actually cross or touch. So this is an example. And again, we could check, right? By taking the partial derivative, which is just cosine of y, we know that, yeah, this is guaranteed a unique solution no matter our initial condition. So again, it's not, uniqueness is not the same thing as a vertical line test. Uniqueness is more of solutions crossing. And again, uniqueness is quite interesting for a differential equation. Well, we'll talk about why uniqueness is so interesting in the next video. I won't get ahead of myself. All right, so until then, enjoy a brief reprieve until your final and most exciting video of this section, where we talk about the applications of uniqueness. What can you do if you know it's unique?